All right, so welcome everyone to this week's What Physicists Do. Today it is my great pleasure to introduce Dr. Isabel Lipartito. So Dr. Lipartito got her bachelor's in physics and astronomy from Smith College before attending UC Santa Barbara for her PhD, which she actually just completed just last week. So if we were in person, I would ask everyone to give a huge round of applause to Dr. Lipartito. That's an amazing accomplishment. So for the students who are interested in attending graduate school, she'd be a great person to direct questions to because it's real fresh in her mind what it's like to be a graduate student. So now she's graduated and is going on to work as a systems test engineer at Lockheed Martin. So she's also a great person to speak to about this transition from academia to industry. So with that, welcome Dr. Lipartito. Thank you so much for being here today.
Awesome, pleasure to be here. Thank you, Alex, for the wonderful introduction. Still getting used to Dr. Lipartito, sounds a little too formal, so you guys can call me Isabel. So today I'm really excited to talk one more time about my work during my PhD, which was developing a new type of camera for taking pictures of extrasolar planets. Along the way, I want to give some history of the field and the state of the art, as well as talking about specifically what I did and how I navigated into a career outside of academia. And it's hard for me to look at the chat, so if you have any questions, please just speak up, don't be shy. So let's start right at the beginning. Exoplanets are planets outside our solar system, found orbiting another star. And I want to first provide a disclaimer that if you see a very nice looking image in this talk, like the one below of the TRAPPIST-1 system, which is 7 planets orbiting a dwarf star, if it looks very nice and sort of artistic, that is probably because it's an artist's conception. When we see an actual image of a planet, it's going to look a little different. But I love these beautiful artistic images just to get inspired and kind of see, like, if we could be right there at the system, what would it look like? So TRAPPIST-1 is a star of many that we have found planets around. So now let's get into a little bit about that history and how it works. Throughout this talk, I want to answer for you guys sort of the large questions surrounding this field. We've talked a bit about what are exoplanets, but really what does finding one mean for us? Why would we want to photograph them? And how exactly are we going to do it? And furthermore, if you're interested in this field or you want to learn more about it, how do research groups in California, across the world, fit into this field, fit into furthering the exoplanet search? So the first planet system that we all know is our solar system. We're in it. And again, this is sort of a composite image. The planets don't really line up like so to take a nice group picture, but these are actual images of the planets just kind of compiled together. And so our solar system, as we know, is comprised of 8 planets. We have our inner rocky bodies, Mercury to Mars, and then we have our outer gas giants, Jupiter to Neptune. And of course, we have some dwarf planets. If you recall, Pluto is demoted to dwarf planet. It's no longer a planet. As we learn more about our solar system, sometimes we change the way we classify things to make sense with new information. But really, how common is this setup? How common is it to have 8 bodies that are diverse in their composition? Is our sun the only star with planets? Is our sun the only star with 8 planets? When we're looking to find more systems, really we're probing, how do we fit in the greater picture? Is our setup an aberration or is it the norm? What other systems are out there? And really, what is the history? What is our history? By looking at systems perhaps earlier in their formation, we can sort of trace back to what did we look like earlier in time? How did we get to this structure? So I also want to remind us that even though our solar system is all we know, and it's our world as far as we can perceive, there are infinite worlds out there. The Hubble Deep Field is an image taken with just about 10,000 galaxies, and this is just a small piece of the sky with thousands of stars in our own galaxy, with thousands of galaxies in our observable universe. There's got to be something out there that tells us a little more about where we came from. And moreover, there's got to be a way for us to understand how really do we fit into the larger universe as a whole. So I think we've touched on this a little bit, but why do we care about finding exoplanets? To greater characterize systems, to greater understand what types of planet-star systems out there, and also to try to piece together our own history and maybe our own future by finding analogs to our solar system. And I'm sure at the back of everyone's mind is the question, is there extrasolar life? Could we find a habitable planet? Could we find a new form of life? If we do, I really hope they're as friendly as the Pixar aliens and not really War of the Worlds, more Toy Story. So Earth exists in what we call the habitable zone. Well, it's habitable for us, carbon-based life forms that depend on water and oxygen. Planets that are too close to their star are going to be too hot, and they're not going to be able to sustain water on their surface. Planets too far from their host star are going to be too cold. They won't be able to sustain liquid water, and the temperatures would be too cold to sustain life as we know it. And the habitable zone has sort of some wiggle room. I'm sure as you guys know, even on planet Earth, there's different habitats. I'm from Florida, so maybe some people would not consider Florida to be in the habitable zone because it is 100% humidity and there are giant lizards walking around everywhere, alligators. And then, but then some humans function very well in what I would consider to be too cold, like Siberia. So there's some wiggle room, but really what you need is the ability to sustain liquid water and an atmosphere that can support oxygen and ozone. And so we are being very human-based when we talk about extrasolar life. If you use your imagination, perhaps there's life forms that could exist very differently from humans. But right now, when we're looking for a habitable planet, an exo-Earth, we define it as life as we know it. So we're looking for something that could support conditions just like ours. If you think about the history of astronomy, it really is going from a sort of point in time when we really thought us humans were the center of it all, to just learning about how small we are in the grander scheme of things. Copernicus was one of the first to postulate that we actually aren't a geocentric universe. Not everything revolves around the sun. Moreover, we are just one of many bodies orbiting a sun. Kepler discovered the mathematical laws by which the planets orbit. No longer were planets thought to orbit in perfect, beautiful celestial circles, but rather they obey ellipses. That's imperfect. And Galileo discovered that there are moons around Jupiter. We're not even the only planet with a moon. So we've been going further and further from this sort of idea that the Earth is unique, the Earth is the center of it all, and just realizing we're one planet going around a star, and there could be millions like us. This sort of came to a head in the early 90s when we actually discovered exoplanets. Now, we've been thinking that other stars must have planets. That's sort of this trend to understanding our own universe. But it wasn't till the early 90s that we discovered exoplanets. In 1992, 2 planets were found around a pulsar. And so that's pretty interesting. These planets must have been radiated and incapable of supporting life. So we found planets around a dead star. Not a bad start. In 1995, we one-upped ourselves and we found planets around a sun-like star, 51 Pegasi b, orbiting star 51 Pegasi. And so that sort of opened the floodgates to finding up to the thousands of planets today. When I talk about the early discovery of planets, these were not imaged. These were found indirectly. Particularly, these were found through the radial velocity method. Now, if you recall from your intro physics courses, 2 bodies orbiting each other exert equal and opposite gravitational forces on each other. They are going to orbit a common center of mass. Now, if you have a star and a planet system, naturally the star is going to have a much smaller orbit than is its planet, due to the difference in mass in the bodies. But nevertheless, the star is going to be moving all the same. If we are looking at it on axis, it's going to kind of look like the star is wobbling periodically. As it's moving towards us, light coming from the star is going to be blue shifted. That's the Doppler effect. As it's moving away from us, that light is going to be red shifted. If we're looking at a star and we notice that its spectra is swaying periodically with time, then we can possibly determine that it has a companion orbiting it. Moreover, the period of the spectral line shifts and the magnitude give us some information as to what is this system, what is the nature of its secondary companion, could it be a planet? Keep in mind we also do find binary stars this way, but we need a little bit more precision to find planets. Another indirect method I want to bring up is the transit method, which came a little bit later, where if we periodically observe a star, if we notice a dip in brightness, then we might think that a body has passed in front of the star. It has transited. And so if you know about the TESS satellite and the Kepler satellite, these are satellites which look for planets using the transit method. They stare at thousands of stars looking for these dips in brightness, which are a signature that a planet is passing in front of the host star. Similar to the radial velocity method, the transit method does need an alignment between the planet and the star. In fact, the planet needs to pass in front of the star to some degree. And of course, with the radial velocity method, you need to be looking in a way, the orbit needs to be aligned in such a way that we are going to see the host star wobble with time. If we were looking a bird's eye view, we wouldn't be able to see those spectral line shifts. So these methods are a little imperfect in that they do require a certain alignment of the system. But nevertheless, we have found thousands of systems through the radial velocity method and the transit method. I want to show you now one of my favorite diagrams. This is from the Exoplanet Archive at Caltech, and it's a dynamic diagram. Every few months, if you look, there's more dots. This is a map of all the extrasolar planets we have found using various methods, the 2 main ones, of course, being the radial velocity and transit method, and they are plotted according to the planetary mass and their period around the host star, which relates to how far are they from the host star. You will notice both radial velocity and transit method are sort of biased towards larger mass planets, which leave a bigger imprint, and also planets which are closer to their host star. Only a handful of planets have been found through imaging. In fact, you can just count them off the diagram. And moreover, these planets do tend to be larger. These are above Jupiter masses, and they tend to be farther from the host star. And so already we can see from this diagram that imaging can probe a different parameter space. Imaging is sensitive to planets from the host star. So that's already pretty good. If we want to fill in this diagram further, it looks like imaging is a way to go. But also not many planets found through imaging. There must be something about it that makes it incredibly difficult. Right now, I just want to point out that when I talk about exoplanets we have found through whatever method, these are in this local cone, just kind of beaming out from our solar system. We are not looking at planets in other galaxies. We're not even really looking at planets in the other arms of our Milky Way galaxy. Finding a planet is so difficult that we are still constrained to finding planets very close to us. I won't quite address it in this talk, but there are methods out there which are going to be able to find planets very far from our solar system. For example, the microlensing method. So if you're interested in that, I encourage you to check it out. It's another very exciting way to find planets, such as the one in yellow on the diagram. So now let's talk about direct imaging. And I'm confident all of you have seen a directly imaged planet. All the images of our solar system planets are through direct imaging. Now, you might be more accustomed to seeing them in reflected light. That's the left image of Jupiter. So that's imaging the visual light that planets like Jupiter reflect off their surface. But planets have their own internal infrared radiation left over from when they were formed. In fact, planets are much brighter in the infrared, about 2 orders of magnitude brighter. So while we are able to image our close family, our solar system planets in reflected light, when we talk about imaging planets outside our solar system, it is 99% of the time in infrared internal radiation because they are so much brighter. It's going to be a little while longer before we can image extrasolar planets in reflected light. And we have had success with direct imaging. I want to show you guys right now my favorite movie of all time, HR 8799 in motion. So TRAPPIST is sort of the, which we saw earlier, is sort of the benchmark system for the transit method. But for direct imagers, HR 8799 is our benchmark system. We have successfully directly imaged a sun-like star with 4 planets orbiting around it. And moreover, we have gotten to the point where we are characterizing these planets. We understand what are they composed of. So this movie is actually a series of images taken over the course of 7 years using the Gemini Telescope made by Jason Wang and Christian Maroy from Caltech. And the star is blocked off with a sort of circle added in post-processing. And the planets themselves don't look as fantastic as that image of Jupiter I showed before. They're just sort of bright blobs orbiting the star. In fact, if you don't look at it for a long time, it might be hard to see these planets against the varying pattern of residual starlight. If you watch the movie for enough time, eventually you get accustomed to it. This just goes to show how difficult it is to image extrasolar planets. We are at the point where we are just making them out in an image, and it's going to be a lot more work to actually characterize them, but we have our methods. I want to talk now about everything that goes into making a movie like this. Sorry, my dog's a little excited. I also want to mention now that sort of the power of direct imaging is you immediately get an image of the system. From this image, we know how far are the planets from the host star, and this movie tells us how does their orbit look? How are they moving with time? That's one of the advantages of direct imaging. And we have the light of the planets. We've captured it. And so, as you recall from physics, light can tell us a little bit about what is the composition of the body that emits that light. All of us, whether we're planets, humans, kitty cats, we all have our own spectrum. Humans radiate in the infrared just as planets do. We're dimmer than planets, of course. And so you can capture an image of a mammal with infrared light, just as you can capture an image of a planet. And if you put that light through what is known as a spectrograph or a prism, so to speak, you can break up that light into its components. I like to use the Pink Floyd album cover as a demonstration of this. Maybe it dates me a bit, but that's the first thing I saw that sort of explained how light works as a kid, and I think about it ever since. Light is composed of many wavelengths. We can only see the visual as humans, of course, but there is infrared and there is ultraviolet and many other wavelengths of light above and below. So if we took light from a planet and we put it through a spectrograph, the idea is the light that the planet radiates is going to pass through its atmosphere. There's molecules in the atmosphere, hydrogen, ozone, carbon dioxide. Those molecules are going to absorb a certain wavelength of the light. And so when we get that spectra and we analyze it, we're going to see missing chunks that those molecules took before that light could get to us. And so we can kind of do some detective work to understand what is in this planet's atmosphere. Is it like Venus or Mars, where there's only carbon dioxide? Or is it like Earth, where it has hydrogen and ozone? By looking for these biosignatures, evidence that these molecules exist in the planet's atmosphere, we can determine which planets might be supportive of life. And so again, this is for planets in our solar system, bit of an easy target, but the hope is to do this for planets across the universe. So what do we need to study planets to make that excellent movie we saw of HR 8799? Well, your basics, you need a camera and a telescope. Maybe something a little bit more high-tech than our Kodak disposable. So we saw earlier, there's only been a handful of directly imaged planets. And moreover, even just looking at a directly imaged system, it's a little bit difficult to pick out the planet. The analogy that we like to say is imaging an extrasolar planet is like trying to find a single firefly in a fully illuminated football stadium. I want to introduce the concept of contrast, the brightness ratio of the planet to the host star. That can be of order of magnitude 1,000,000, it can be order of magnitude 1,000,000,000. And so it is our responsibility to find that faint glimmer of light against the giant fusion powerhouse that is a star. Moreover, complicating this is, for the most part, we are observing on Earth. So that means that the light has to go from the planet, go through space, and enter our atmosphere. Our atmosphere is a constantly changing array of pressure gradients and temperature gradients that fluctuates on the order of microseconds. They serve as a series of infinite mirrors which scatter out that starlight and really change the sort of tight star image that we would like to see, which is referred to as an Airy Ring, sort of smear that out, spread it across the image until it is something as turbulent and discombobulated as we can imagine. We need some way to correct for that before it gets into our image, and we really have no hope of seeing the planet against this smeared out starlight. We have what is known as an adaptive optic system. Every telescope, especially ones that do high contrast imaging, have them. An adaptive optic system is comprised of a wavefront sensor, which actually senses the distorted wavefront of light coming through the atmosphere, sends signals to a deformable mirror, which actually adapts and changes to perfectly cancel out the distortions in that wavefront. And then part of that light is sent to a high resolution camera in real time. The image is being continuously corrected. So naturally, this works really well. There are some limitations due to the fact that the atmosphere changes on a timescale greater than the loop between the wavefront sensor and the deformable mirror. Some distortions are not going to get corrected because they occur at too great a rate. And also, there are some different paths that happen. As you can see, some of the light is split to the camera, some of the light is split to the wavefront sensor. There's going to be some path issues that lead to residual bits of scattered starlight. But for the most part, this works incredibly well. For example, take a look at this image of Ganymede taken with and without adaptive optics. Without adaptive optics, it's just sort of a bright smear, but with adaptive optics, we can actually make out features on this moon. Once you have collected your starlight into as tight a point spread function as possible, then you want something to block out the star. And now this is a sort of cartoon graphic to illustrate the power of a coronagraph. Now, it doesn't quite work that way. We don't have a graduate student with a popsicle stick and a piece of paper trying to block out the star in front of the telescope. It is a sophisticated piece of optics. But I sort of like this image because it really shows the natural response of humans to bright light sources. Something's too bright and we can't see what's beyond it, we put our hand up, we put our coronagraph up and block out the star. And it works really well to leave the exoplanets visible. We don't want that starlight entering our image. So adaptive optics and coronagraph serve very well to increase our chances of seeing the planet, brown dwarf, high contrast target. But in our image, as we saw in that HR8799 movie, there still are residual atmospheric aberrations known as speckles. This is a movie of different images of brown dwarf HD 1160b that was actually taken by one of my advisors using the Keras instrument. We'll talk about that in a little bit. So the movie increases with wavelength. So this is a picture of the system taken in different wavelengths, different colors of light. And you can see a pattern of a sort of cross. Those are calibration marks made by the camera that are used later in trying to photometrically calibrate our images. But don't worry about those too much. What I want you to focus on is the pattern of scattered starlight, the speckle pattern that envelops the brown dwarf. In fact, without that circle, the red circle around the brown dwarf, you wouldn't really know it's there. So even with a coronagraph, even with adaptive optics, we still have residual speckles. We need fancy techniques after the images are taken to further remove the speckles. The speckles of light actually are chromatic in that their placement on the image depends on wavelength. If you're watching the movie, the speckles appear to move out radially with wavelength, whereas an astrophysical body like a brown dwarf, a planet, a star is going to stay put. So using a clever technique known as spectral differential imaging, we actually can take multiple images of a system in different wavelengths of light, and we can scale the speckles so to subtract them out. But because the astrophysical body we're interested in detecting doesn't change with wavelength, that actually will remain in our images, and we can get a final image that clearly shows our astrophysical body. That was used to make the HR8799 movie that we saw earlier. So the state of the art, even with coronagraph, even with adaptive optics and fancy image processing techniques, we are limited to finding exojupiters beyond their star's habitable zone. A larger planet has a greater light in the infrared, And also looking for a planet far away from the host star is a greater chance of detecting it because it is out of that pattern of residual starlight. So we're still not quite at the point where we're finding exo-Earths. We're just finding big, faraway planets. Still a great accomplishment. So I want to talk now about the push to expand this field to the point where we're finding exo-Earths. And there's multiple fronts. For example, we are building larger telescopes to enhance our light collecting power. A telescope is a bucket for light. So the bigger the bucket, the more light you can collect. For example, here is an image of the Andromeda Galaxy. From top to bottom, a different telescope was used with a bigger diameter. Even with the same collecting time, there is a much deeper, detailed image of the Andromeda Galaxy in the bottom image than in the top. A larger telescope also improves your resolution. So the resolution, or the finest detail you can make out in your image, depends on the diameter of your telescope. To the left is an unresolved blur of two light sources, and then the right is a resolved image where you can see both of those light sources, a bigger diameter. And so if we're trying to probe to find planets closer to their host star, a bigger telescope will improve that resolution. The planet isn't going to be swallowed by the star. For example, you might have heard about the 30-meter telescope. That, of course, in the name, it's going to be 30 meters. That is, I am sorry. My cat wanted to join us. Sorry about that. He really loves when I give talks. It's his time to shine. So as I was saying, the 30-meter telescope is not built yet, but the idea is this will be large enough to find exo-Earths, a 30-meter diameter, great amount of light collecting power, and an incredible resolution. The problem with building bigger telescopes, though, is we don't always have the right to put them where we think we should. Telescopes do best on remote mountaintops, away from the light of cities, and also high up, so we are less bound by weather patterns and the atmosphere is thinner. But it takes up a lot of space and a lot of resources, and we don't have the right to put telescopes on land that doesn't necessarily belong to us as astronomers. So while the 30-meter telescope might still get built, it's not our only option for pushing to higher contrast, for finding exo-Earths. We can also build a better detector. So I want to talk now about my work through the Mazin lab at UCSB. PI Ben Mazin, he is the one to the right wearing the blue shirt. So Ben has mentored me for 5 years now, and through him, I have learned about the power of building superconducting detectors for exoplanet direct imaging. So in this image, of course, you can see all of us, and we are surrounded by a lot of gear. There's a lot of wires, there's a lot of metal, and so we'll talk about why all that is there in a little bit. First off, I want to talk about this technology, the superconducting detector technology. So these are officially called microwave kinetic inductance detectors, or MKIDs. So the acronym may not exactly make sense right now, and we'll talk, except for the detector part, we'll talk about what each of the words mean. It is a bit of a difficult acronym to explain because it can be a bit misleading. But first of all, this is what one of them looks like, sort of an artistic photo. It is a small detector, can fit in the palm of your hand, about the size of a quarter. But this little piece of technology has a lot of power. Most cameras that we interact with on a day-to-day basis are semiconductor based. Your cell phone camera, your digital camera, they operate on the photoelectric effect. Every single pixel I like to think of is a bucket filled with electrons. And when a photon or a particle of light drops in that bucket, it releases about 1 electron. We read this electrical signal and we can figure out about how much light is arriving in a pixel in a given exposure time. This doesn't enable us to get any information on the energy of the photon, nor do we really get a timestamp of when the photon arrived. But of course, we can make a picture in a certain wavelength of light. Well, microwave kinetic inductance detectors I like to think of are sort of like a racetrack where every single car is an electron, right? And so the electrons are racing around the racetrack with very, very minimal resistance. And when a photon arrives, it's sort of analogous to if you threw a very energetic bouncy ball right in the middle of the Indy 500. It is going to cause an event of which we can pinpoint the exact time at which it started. And we can, by the magnitude of the pileup, we can get some information as to what was the energy of the bouncy ball thrown onto the racetrack. So a bit of an odd analogy, but bear with me. Microwave kinetic inductance detectors, every single pixel is a superconducting circuit. So a superconducting LC circuit, inductor and capacitor. The electrons are whizzing around the circuit with minimal resistance. They are paired up into what is known as Cooper pairs. And so when a photon strikes the inductor, we direct it onto the inductor, then it actually breaks up a bunch of these Cooper pairs, releases some energy, but also breaks up these Cooper pairs into what is known as quasi-particles, loose electrons. That changes the inductance of the circuit. This is the kinetic inductance part of the MKid acronym, the kinetic inductance effect. Now that change of inductance is important. If we were thinking ahead, which we do, and we were continuously probing these circuits with a microwave probe tone, then we would see that probe tone come back to us slightly shifted off its resonant frequency because the circuit we're probing had a change in its inductance. And this is the microwave part of the acronym. We are continuously probing these circuits with a microwave probe tone, and we are searching for shifts in that probe tone indicative that the circuit underwent a change in inductance, indicative that a photon hit. Moreover, we can pinpoint the arrival time of that photon, and we can roughly get its energy because the number of Cooper pairs broken, hence the shift in inductance, hence the shift in resonant frequency, is proportional to the energy of the incident photon. So a bit of a mouthful. It is, I always kind of feel like the guy in the It's Always Sunny in Philadelphia show when he's like this, trying to explain them kids. But it's sort of like a chain reaction, and it enables us to get a product that is a list of photons with their X and Y spatial information, what is the coordinate of the pixel they landed on, but with a rough sense of their wavelength, their color, and their arrival time. So here's kind of just a fun cartoon mock-up I did, but really millions of photons are arriving at any given instant, particularly if we're observing stars. So these lists are quite big. Our energy resolution is low order. So we have the wavelength of a photon plus or minus about 100 nanometers. So not as precise as other spectrographs on the market, but precise enough if we wanted to low order characterize a planet's atmosphere. And so our data products are four-dimensional: time, two spatial positions, and energy. And so that gives us a lot of options. We can make images. We can make light curves. We have temporal information. We can make spectra. With just that small MKid chip that fits in the palm of my hand, we have something that is a photon counting detector, a camera, and a spectrograph all in one. And that's sort of the magic of these detectors. If you have a traditional CCD or CMOS camera, you need an additional set of optics to convert it into a spectrograph. But with MKids, we get that information for free. Well, there is a cost. The cost is, there's a lot of entourage that goes in. As you saw that photo of us standing in the lab, it is a lot more than that unencumbered detector. So what we do, our MO in the Mazine lab is we build MKit instruments and then we take them all over the world, well, all over California, and we use them ourselves. Ordinarily, when you go to observe at Palomar Observatory, at Subaru Observatory, you apply for time on a specific instrument. But for us, we show up with our camera and we're like, we brought our own, we're good to go. We've coordinated it with the observatory ahead of time, of course. But what's being exciting is not only do we do astronomy, but we do astronomy with our own products that we built in-house at UCSB. So earlier I showed you guys a picture of an MKid chip, and here's another one. This one is a little bigger. It actually is for a different instrument than the first one, but same idea. A chip that can fit in the palm of your hand goes in the telescope, along with all of its gear, which we'll talk about in a little bit. In this image, you can see that our beautiful rainbow chip is in a gold box. That actually is how the microwave probe tones are going to be sent in and out of this chip. All of those snaking lines that you see, there are 10 in this one, are microwave feed lines through which we send the microwave signal to the MKids and then read it out to sort of start that process of continuously sending a probe tone and looking to see if it is shifted. And so what we do is when we arrive at a telescope, we put all our gear in the basket of the telescope and it rides around in the basket. If I extended that image to the upper left, it would be open to the sky. And we usually take about a month to set up at Palomar, and then we spend a few nights on sky observing, looking for planets, looking for binary stars, looking for brown dwarfs. So now to talk about the entourage. So I mentioned that there's superconducting detectors and there's some fancy electronics. Well, that MKid chip is actually built into a giant refrigerator. The Mazine lab has 2 instruments for exoplanet detection. The left one is called Darkness. That is the one that went to and from Palomar from 2016 to 2018. And then the one on the right is MEC, the MKid exoplanet camera. This one is currently installed at the Subaru Telescope in Hawaii. And so those chips are placed into these giant refrigerators because in order to observe the superconducting effect, the camera needs to be cooled to 100 millikelvin. So on the left, you can see Darkness all packed up. There is a very strong metal shell around it because we need to cool it down to 100 millikelvin and take it to a very low pressure, hence the really strong shell. On the right, you can see graduate student, well, now Dr. Alex Walter in front of the MKid exoplanet camera. This is without its shell, so this is kind of what it looks like on the inside. The MKid chip is mounted to the sort of pointy base of that detector, and then it can be placed inside its shell for cooling down, for depressurizing. And then from there, we send in all the electronics. And so this is an example of a full instrument. This is a CAD mock-up. To the back, you can see a cartoon of MEC. And then surrounding it are the optics table in front of it to guide that light onto the MKid array. And then also a giant electronics rack, which is for mech is about 9 feet tall and 900 pounds, because we need to have the infrastructure in order to continuously send microwave probe signals to about 20,000 MKids and continuously read them out. We don't lose time to read out. This is a continuous loop. So there is a lot of firmware and hardware that goes into play into sending in that signal and reading it, looking for those shifts in the microwave probe tone indicative that a photon arrived, and also determining the nature of that photon. So quickly, when I joined this lab, I thought at first I'd be doing astronomy, but I'm very glad that I got to do so much more. There was a lot of nights of hardware, of literally mounting things into a telescope and hoping that it wouldn't fall out when the telescope moves. That was quite fun. There was I actually built the electronics rack for mech, so I got to learn a little bit about signal processing, about firmware and software, and wiring, soldering. Basically, how do signals originate? How do they get sent through? And how do we process them? So what's fun about working in a group that's joint instrumentation and joint astronomy is you get to see the best of both worlds. You get to see how are the instruments made and how do we use them. So keep in mind, all of this goes into a telescope, a bit heavy. And so I talked about the darkness instrument that we took to and from Palomar for about 2 years. And all the while we were building the mech instrument, the MKid exoplanet camera, which is permanently installed at the Subaru Telescope in Hawaii. Now that's very nice because it is about a month to set up an MKid system and make sure all the electronics are working, make sure that it is bolted into the telescope undercarriage. Mech is permanently installed, very nice for us. We can basically just log on remotely from UCSB, power it up, and observe over the course of a night. What's really cool about the Subaru Telescope is there are a variety of instruments, not just mech. And one of the main goals of the Subaru Telescope is to find and characterize planets. So I mentioned that MKids are cameras and they are low order spectrographs. So kind of our hope is mech will go on sky with maybe a more powerful, a more high resolution spectrograph like Keras, which we saw an image from a little bit earlier, that brown dwarf speckly image. The idea is mech will tag team with Keras. Mech will detect and do a brief characterization, and we will send that light to Keras for a full characterization. We've come a long way since 2016. We've come from that kind of quirky group that builds these crazy detectors and keeps knocking on the Palomar door to set them up. We've actually gone mainstream, and we are working with a variety of exoplanet groups across the country. The hope is that mech and future instruments will be a mainstream instrument that anyone can apply for time on to use. And that our data will not just be used by Mazine Lab and Mazine Lab graduate students, but by astronomers across the world. So I talked a lot about finding planets, and then we launched into the instruments we're building to find planets. But really, I want to emphasize that this is a continuous work in progress. MKids are a little bit tricky, not just that they have to be cryogenically cooled down, but because we are working with some extremely complicated condensed matter physics. And as you can tell, I'm a bit more of an astronomer, but I do encourage you to check out other papers in the Mazine Lab, which explain the condensed matter physics behind this a little better. At any given moment, right now, maybe about 40% of our pixels, 40% out of 20,000 work. And we run into many issues. We could lose an entire night just because the electronics won't boot up. This, as all technologies go, this is a work in progress. As of 2019, when we first got mech to Subaru, we first got it on sky observing, we were limited to observing star systems. We don't quite have the contrast to detect planets yet with mech, but we are continuously improving. That was also true for darkness. This is one of our success stories. This is the trapezium star system. It's actually 4 stars, B1, the main star, and then surrounded by a binary, B2 and B3, and then a faint star about 1,000 times fainter than the primary, B4. In this image, you can see, in addition to the labeled stars, there's sort of a box-like pattern that, similar to what we saw in the Keras image, is calibration dots. So those aren't part of the star system. But this was one of our first big successes. I've talked about this technology very confidently, but keep in mind, when we turned mech on for the first time, we had no idea if it would really respond coherently to light. So just being able to see this star system and get back the image we're expecting to get was incredible. We could see B4, which is 1,000 times fainter, and we can actually just resolve the binary B1, B2, and B3, which are incredibly close on sky. Mech was ready for astronomy, but unfortunately, it was not quite ready for planets circa 2019. We are limited right now to seeing things about 1,000 to about 10,000 times fainter than the primary star, good for observing binaries or multiple star systems, but not quite there for observing planets. But fortunately, the technology continuously improves. Even after I left the Mazine lab, we are developing better MKid detectors. We are refining our image processing techniques, because the hope is, because we have built an instrument that is a spectrograph and an imager and also a photon counting detector, we have the ability to probe to find extrasolar Earths. Oh, I'm sorry, having a bit of allergies, in the future. And provided also we are working with high contrast, high resolution spectrographs. So I want to end here, and I am happy to take any questions about anything I've talked about thus far. Thank you for your time. And again, I'm grateful for the opportunity.
All right, thank you so much, Dr. Lipartito. That was really amazing to hear about all the great work you guys have been doing. So if anyone has any questions, you could perhaps raise your hand, or if you prefer to type your question in the chat, that also is great. So if there aren't, I don't see anyone right away. So maybe, oh, sorry, Scott, I didn't see your hand up.
I'm sorry, I had it up and then I realized maybe you didn't see it, so I'll do it with the icon. But I've just got a thank you, Isabel, for that talk. It was wonderful. It's super exciting because it's a field, not the MKids, but the extreme adaptive optics that I worked in for a great deal of time. Locally, we have adaptive optics lab, but we can't work in the extreme regime anymore. We're an undergraduate institution, and our access of telescopes to do that kind of work is limited. We're at one meter class telescopes, but we do some fun things here. But seeing your work, I just wanted to thank you for it. I wanted to mention to our students that are watching that this is something that I like to mention to students, because we often talk about Copernicus, Kepler, and Tycho Brahe, and And I try to tell people that Tycho Brahe and being the technician to figure out the technology to make the more precise measurements is a kind of work that you can do. It's clear that you guys are pushing this forward. Isabel, you've played this important role in making our ability to make these measurements more and more precise. And I'd like the students to see that. And I got such a sense that you enjoy this work. Can you talk about the transition coming in as someone interested in astronomy and finding that you enjoyed so much working on this technology side?
Of course. Yes, thank you. Thank you for bringing that up. That's a very good question. So I'm trained as an astronomer foremost. I got into Ben's lab by a bit of an accident. I was working in pure astronomy originally, and I had two good friends who were in Ben's lab, and just hearing about everything they did on a day-to-day basis, I was like, ooh, I want to do that. And then, yeah, just I found Ben one day, and I was like, yeah. would you like an astronomer? And fortunately, that we were starting the exoplanet push at that point. I didn't quite get into it. MKids can be used for any form of astronomy. We have done pulsars in the past, as a side note. But Ben let me know. He was like, well, immediately we're not getting exoplanet data. We're still building darkness. We're still building NEC. Are you comfortable doing some engineering for a while? And I was like, yeah, sure. A lot of it I learned on the spot. Ben would say something to me. He'd be like, solder this. And I was like, YouTube, how do you solder? A lot of instrumentation is people just with a passion for building, and some in the technical, if you're willing to learn the technical side of things from friends, from colleagues, even from YouTube, it is more than doable. It's just a matter of, being careful. Don't connect two wires you're not entirely sure should be connected. But if you have an experimental mindset, this is more than attainable. In fact, as you guys can see, I enjoyed the building, I enjoyed the testing so much that when I was thinking about what to do after PhD, I found that I would fit in really well in the aerospace defense industry. I met some people who work at Lockheed, and when we got to talking, I found, wow, I do about the flip side of what you do. They were of course working with semiconductors, but I could relate so much. And I found that a lot of what I'm passionate about, which is building new devices, testing new technologies, troubleshooting strange problems that we didn't expect, would be very translatable. So if you have the skills, it's you're more than ready to transition.
Great, thank you. So I think our next question was from Jay Robert here, who's raising his hand.
Hi, thank you. First of all, I just want to say what an amazing talk, just perfectly pitched at the undergraduate level. So I'm curious about the resonant part of it, and how long does the Cooper pair stay broken up, and how do you count how many photons have come through? And then the third question, if you're up for it, can you run the thing backwards and get a photon out?
Never thought about the third question before.
Okay.
No,
that's my job.
The first two, so the Cooper pairs stay broken for the order of microseconds. So what happens when we have a photon event, as soon as a pixel triggers on a photon, we lock all other photons out for 10 microseconds. That is called our dead time. And so that is enough time for the entire circuit to reset after the photon event and be ready for more. So in post-processing, we actually have to correct for that dead time and extrapolate how many photons would have arrived. On looking at a single star, the order of magnitude of photons arriving per second is 100 over a millisecond. but our timestamp is to the 10 microseconds of precision. And running it backwards to get out a photon, I don't think so, because when you have the Cooper pairs broken, they release some energy in the form of phonons. So putting the Cooper pairs back together, I think, is just an energetic release, not necessarily in the form of usable photons.
Great, thank you. So I noticed we had a question in the chat from Doug Clark, who asks, can you show a typical spectrum? So I don't know if you happen to have one available, or tell us the spectral range for the MKid device. And he also says, great talk, thanks.
Oh, thank you. On hand, I don't have one, but I can say that our spectral sensitivity for MEC and also for darkness is about 900 to 1400 angstroms. Sorry, nanometers. I always confuse the two. So this image is what would be known as the Y band. So that is about 900 to 1100 nanometers.
Great, thank you. So we're already a couple minutes over, but maybe if there was one more talk. Oh, it looks like John has a question. Would you like to go next? It looks like you're still muted.
Am I through now? Good. Well, I have one observation and then a question. Is when I started graduate school, photomultiplier tubes were in vogue, and they needed multiple photons to fire. Single photon events we had real trouble with, and they work better in the energy rich spectrum, in the blue or ultraviolet. So this is you are, I won't say you're light years ahead of me, but I'm very impressed. The question is, what is your new job? What does that entail?
So I actually kind of know what I'll be doing. I interned at Lockheed Martin over the summer, which is a tip I would advise if you go to graduate school and you know you want to transition into industry, government. It's not a bad idea to see if you can take a summer off and intern at a company. I know people who've interned working in policy. That's also a career option, just to make sure that this is what you want and you like it, but also B, to kind of get a foot in the door. A lot of industry internships lead to a job offer, which is fortunately what happened for me. So I was able to front load the job search into an internship search and then their segue into a full-time job. When I was at Lockheed, I can't give too much details because I am under security clearance, but basically similar to what I talked about, getting a very precise camera ready for observations. So anything from building some electronics for it, to taking a camera and putting it under light, testing it, seeing its response. There was a problem with one of our cameras in that it was picking up a weird signal. So I was able to use some of my signal processing background to actually model and subtract out that signal. What I really like about working at Lockheed, and I imagine that's true for many defense aerospace, is on a given day, you can do many different things. You can be in the lab, soldering, screwing in screws. You can be doing some coding if you want to sit down, take a break. So it's a very dynamic job, and you get to meet a lot of interesting people with different backgrounds.
Thank you.
Awesome, thank you so much. So I think since we're already 5 minutes over, we'll stop there. So let's thank Dr. Lipartito again. I'll give a big round of applause on behalf of everyone in the audience. So thank you so much for the excellent talk. For everyone, next week, we will not have a talk because it is spring break at Sonoma State. But then the following week, we'll come back with Dr. David Ramirez, who's going to talk about black holes and superconductors, I think. So it should be a really interesting, awesome awesome talk. So thank you again, Dr. Lipartito, and thank you everyone for coming.
Thanks, everybody.